So, in today's class I am going to talk about Laguerre polynomials and how they appear in the solution to the radial part of the hydrogen atom problem in quantum mechanics. Okay. So, let us just remind ourselves. So, what is the the wave function for the hydrogen atom depends on r, theta and phi, okay, and this is written as a product of a radial part that depends only on r times an angular part that depends on theta and phi, okay. And this angular part, okay, we already saw the solution of the angular part, okay. So, this was related to the angular momentum eigenfunctions, and these are related to the spherical harmonics, and they have these two quantum numbers L and M, okay. L and ML probably is probably the right notation, okay. So, these are related to associated Legendre polynomials. You can solve these using the power series method, okay. Now, the radial part, okay, so the radial part is what we are going to focus on today, okay. So, let us write the Schrodinger equation, okay. I will write it in spherical polar coordinates, okay, and I will just write the expression, okay, h cross square by 2 m, me is the mass of the electron, and I have r double prime plus 2 by r prime plus, now the angular part, okay. So, the angular part, since you know the solution, we use that solution and write this as L plus 1 h bar square divided by 2 me r square times r, okay. And then you have an additional term, okay. So, that looks like E square. So, all this comes from the kinetic energy, then you have the potential energy E square by 4 pi epsilon 0 r times r, this is equal to E times r. So, the left hand side is the Hamiltonian times operated on r, and the right hand side is E times r. Remember, r is a function, this capital R is a function of small r, okay, and r double prime is just d square by dr square, and r prime is d by dr, okay. Now, I will just rearrange this a bit, okay. So, just take this minus h cross square by 2 me to the right side and then just pull everything over to the left, okay. So, I get the differential equation in the following form: r double prime plus 2 r prime by r, okay. So, this is the only term that so since I took this over here, okay, so this is the only term that has r double prime and the only term that has r prime, okay, plus, okay. Now the h cross square by 2 me will cancel with this, okay. So, you have minus h cross square by 2 me and you have h cross square L plus 1. When you write the remaining terms, okay, now I will have 2 e multiplied by 2 me by h cross square, okay. And what I will do is I will take this factor over there, okay. So, I will write this in the following form. I will write this whole thing multiplied by r equal to 0, okay. So, what I want to do is to write something multiplying r, okay. So, since I just want r, okay, what I will write is the following. So, I will write 2 e by a e square, okay, times 4 pi epsilon 0, okay, plus 2 by a r, okay. I will tell you what a is in a minute, plus L plus 1 by r square, okay. So, a is the Bohr radius, okay. So, a is the Bohr radius, okay, and that is related to h bar square times 4 pi epsilon 0 divided by m e square, okay. So, this is the a, okay. So, I just use this and rearrange things in a bit to write it in this form, Okay. Now don't worry about all these constants, okay, but what is important is that this looks like a second order differential equation, okay, and it is something that you can solve using the power series method, because you notice that this has a 1 by r. So since I have a 1 here, okay, so at r equal to 0, this does not vary, this does not go to infinity faster than 1 by r. Similarly, I have a 1 by r square, okay, that is the highest power of r, and that does not go to 0 faster than 1 by r square. So basically with this you can see that you can apply the Frobenius method about r equal to 0. Okay. Now you can apply the Frobenius method about r equal to 0. Okay. So I will just mention this, can apply Frobenius method about r equal to 0. Okay. But instead of doing that, we will make things a little simpler. Okay. So you can do this, but you will get some very complicated recursions. Okay. So instead of that, we will separate some factors, just like we did in the case of the harmonic oscillator. So what we will say is you substitute r of r is equal to e to the minus c r times k of r, okay, where c is equal to minus 2 e times 4 pi epsilon divided by a e square, the whole thing raised to half. Okay. And you can probably see why we took this form, because suppose you take large r. Okay. So suppose you take r going to infinity. So if r is going to infinity, okay, then this term will be negligible. Okay. All these 1 by r terms will also be negligible. So what you will get is r double prime is just some constant times r, okay, and so you will get an exponential decay. Okay, you will get an exponential decay. So it will exponentially go to 0, okay, and that power of this exponential is exactly this. Okay. So the coefficient of the exponent is this, and basically this immediately tells you that E should be less than 0. So the energy of this electron in the hydrogen atom should be less than 0, and that basically says that the electron is bound. Okay, it is not free to go. Okay, so you see this, and when you make this substitution and you substitute in this differential equation, you will get a differential equation for k. Okay, and I will just write what that differential equation is. You can actually go ahead and work it out. Okay, so let us write down what that differential equation is. So it looks like the following: r square k double prime plus 2r minus 2cr square k prime plus 2 by a minus 2c r minus l plus 1, the whole thing multiplied by k equal to 0. Okay, so I wrote it as r square times k double prime plus something. Okay, I do not have just an r k prime, I have a r and an r square k prime, and I have something else equal to 0. Okay, so this is where you can apply the power series method. Again, you can verify that the Frobenius method can be applied. And if you apply the Frobenius method, what you will say is that k is equal to, I am not writing the k of r, okay. So j equal to 0 to infinity b of j r raised to j plus s. Okay, so remember you had x raised to n plus v. Okay, so this is the same thing. Instead of n I am using j, instead of v I am using instead of r I am using s. Okay, the point is so s is what is going to be determined by the initial equation. Okay, I just want to emphasize that if you actually want to solve the hydrogen atom problem, and you want to get what the 1s wave function looks like, what the 2s wave function looks like, and so on, then you have to go through this procedure. So this procedure is actually necessary. Okay, so we usually directly write the solutions, but actually if you want to derive the solutions, you have to go through this procedure. Okay, so what does the indicial equation work out? So if you substitute in this equation, your indicial equation looks like this. So it looks like s square plus s minus L square minus L equal to 0. Okay, and you will get basically two conditions. You will get s equal to L or s equal to minus L minus 1. Okay, so these are the two possibilities that you can get for the indicial equation. Okay, so now this s equal to minus L minus 1. Okay, remember here what it means is that you have a k equal to r to the s times sum over j equal to 0 to infinity bj r raised to j. Okay, so basically when j equal to 0, you have r raised to s. Okay, so r raised to s is a leading term. Now you can actually show that when s equal to minus L minus 1, okay, then you will have a problem at r equal to 0. So s equal to minus L minus 1 creates problem at r equal to 0. Okay, and you can show for various reasons that this is not of interest. Okay, so the solutions that are of interest look the following. So k is equal to r raised to L times sum over j equal to 0 to infinity bj r raised to j. Okay, so this is the form of the solutions that we are actually interested in. So we start with this. Okay, now r raised to L, this is the same L that appears in the differential equation. Okay, if you work it out, then you will get b of j plus 1, you will get a recursion relation. Okay, that looks like b of j plus 1 equal to bj times 2c L plus j plus 1 minus 2 by a divided by j plus 1 plus 2 L plus 1 j plus 1. What is important is that this recursion relation is what you get, and notice that here you have j and j plus 1 are related. So you do not have only odd terms or only even terms. Okay, because the reason is your differential equation had a term that has an r k prime and an r square k prime. Okay, and similarly it has an r k here. Okay, so basically you get coupling between both j plus 1 and j. Okay, not just j and j plus 2. Now we can say that if this series has to terminate. Okay, so if series has to terminate at j equal to, I will just call it k. Okay, then we should have 2c times L plus k plus 1 is equal to 2 by a, or you will get c is equal to 1 by a times n, where n is equal to L plus k plus 1. Okay, so n equal to L plus k plus 1. Okay, now k can be anywhere from 0 onwards. Okay, so L also can be 0, 1, 2, 3, etc. So basically n equal to 1, 2, 3, etc. So these are the allowed values of n. Okay, and also notice that n is greater than or equal to L. Okay, so these will be familiar. So n is what is called the principal quantum number. Okay, and you can immediately see from here that n has to be greater than or equal to L, and n has to be a positive integer. So this is a very nice thing that you got this quantization of n. Now you can go further, because c is related to your energy. Okay, so basically if you substitute for c, if you substitute the expression for c, okay, in terms of E, that is this expression that we had here, okay, so C goes as energy raised to half, so energy goes as C square, okay, and with some constants you multiply all those constants out, okay, and you will get the expression for energy of a hydrogen atom. Okay, so what you will get is that E, okay, goes as, and I will put a subscript n, so it goes as 1 by n square with a minus sign. okay, and you will have E square by 4 pi epsilon 0 a, and if you substitute the value of a, you will get minus 1 over n square, and what you will get is m E 4 divided by 8 h square h, okay, h is epsilon 0 square, okay, and this is the usual energy expression for the bound state. So this is the usual. So if you substitute all these values, you will get it as minus 13.6 electron volts divided by n square. Okay, so you can substitute these values and get this, and what we have seen is that by this procedure we are able to get exactly the energy of an electron in the hydrogen atom. Okay. Now next, what about the wave functions? What about the wave functions? So the wave functions, so your r, now it is a function of n and L of r. Okay, so this has this form r raised to L e to the minus r by n a. Okay, so you can show this, okay, n times a, and you have sum over j equal to 0 to now the series terminates at j equal to k. Okay, so and k is n minus L minus 1. So I can write this as a sum that goes up to n minus L minus 1, and what you have is bj r raised to j. Okay. Now what you can do is you can go ahead and you can express these. Okay, so this is a polynomial of degree n minus L minus 1. Okay, so this is a polynomial of degree n minus L minus 1, and this is what is closely related to something called the Laguerre polynomial. Okay, so the Laguerre polynomial, this polynomial, okay, so you write Laguerre polynomial, okay, L, and L depends on n and L, okay, and the argument of L is actually rho, it is not r. Okay, this is just I mean rho is just a constant multiplied by r. Okay, so rho equal to r by a for the hydrogen atom. Okay, so for the hydrogen atom it is r by a. Okay, and basically I can write my radial wave function of r, okay, as you know, it is proportional to, okay, now I have a rho raised to L e to the minus rho by n, okay, and then I have L n L of rho. Okay, rho is just a change of variables that is used, okay, but basically you can write the wave function in terms of these Laguerre polynomials. Okay, so this is actually called an associated Laguerre polynomial. Laguerre polynomial, just as you had the associated Legendre polynomial. Now I do not expect you to remember all these things about Laguerre polynomials, but as a student of physical chemistry, it is expected that when you see the quantum mechanical problem for the hydrogen atom, okay, you should realize that the radial part of the solution contains Laguerre polynomials. Okay, and if you want, you can go and work it out, you can work out all the details, you can work out all the properties of the Laguerre polynomials. Okay, what we know is that this Laguerre polynomial of L n L, the associated Laguerre polynomial, has degree n minus L minus 1. Okay, and this degree of this polynomial, okay, so the degree of L n L is equal to n minus L minus 1, and this is actually very this degree turns out to be very important, okay, because if you have a polynomial of degree n minus L minus 1, okay, then it will go to 0 at n minus L minus 1 points. Okay, so that means number of radial nodes equal to n minus L minus 1. Okay, and this is a very useful result, okay, that you will see in your quantum mechanics courses. So, the other parts of R, okay, so rho raised to L goes to 0 only when rho equal to 0. Similarly, e raised to minus rho by n goes to 0 only when rho goes to infinity, but it is this Laguerre polynomial, okay, that will give you the different nodes of the wave function. Okay, so again I will stop here. Okay, I just want to emphasize that I've tried to illustrate some of the applications of the Frobenius method. Okay, I don't expect you to remember all the properties of Laguerre polynomials and Bessel functions, but I expect that with this knowledge, okay, you will be able to work them out whenever you need to. Okay, and in these few lectures I have tried to give you glimpses of the applications, okay, but there are several applications. If you read any book, you will see that Bessel functions and Hessel equation, there are several applications. Okay, it is in fact related to all kinds of series like the hypergeometric series or even the Legendre polynomials and so on. Okay, but we have not tried to do all those things. What I have tried to do is try to give you a feel of where this Frobenius method is used in various chemical problems. Okay, and in the last lecture of this course I'll do a few practice problems that had focused on the Frobenius method. Thank you.